Okay. Good. Hello, everyone. It's a pleasure to introduce Nathan de Oliveira Silvano. He has been here for slightly less than 1 year at IFISC as a postdoc with the Maria de Maeztu program. And before, he did his PhD at Rio de Janeiro and working on some problems of field theory description of stochastic systems. And he will present us some mixture of what he did before and what he has been doing here at IFISC. So the floor is yours.
So thanks everyone. Thanks Emilio for the introduction. And thank you all for the presence. Does the people in the Zoom can hear? Because I don't know if this is on.
Yes.
Okay, perfect. So, okay, thanks again. Well, as Emilio said, I'm going to talk to you about some active matter systems today. And the idea is basically to talk about two models. The first one was one of the models that I did at the end of my PhD. The second one is one that we're finishing right now. Hopefully, by the end of February, we have an archive ready. And if I have time, I would like to talk to you about some perspectives for this year, because each of these problems, they are kind of similar, but they were treated in a very different way with different techniques. And the idea here with this future perspective is kind of like pick up some stuff from each one of the projects and do something different. But before I start, I think I need to do some contextualization. I was doing my PhD, as Emilio said, in stochastic systems, working with a group in quantum field theory. But before I lose half of you, I'm not going to put any crazy math here. I'm just going to try to keep the message clear, because as I'm going to show, although sometimes we have a very well-known system, we can discover some different things if we look from a different point of view to the same physical system. And that's, I believe, is my message trying to convince you here to keep the open mind for a different point of view in physics if you're not used to it. So why do I use quantum field theories? Well, basically because I'm interested in describing complex systems, and complex systems have infinite degrees of freedom, and field theories are really useful for describing systems with infinite degrees of freedom. And I can also study phase transitions, critical points, look for universal behavior. And the questions that we can answer using the field theories are essentially like, what is the properties of the fundamental state? I'm putting in quotes the vacuum. I can find out what is the fate of the fluctuations on those states, and study also thermodynamics or mechanical properties. Okay. The only thing that I'm going to show before is that I use, for example, one particular formalism, which is the Martin-Segal-Rose formalism. To be very simple, it says that this formalism allows me to get any stochastic equation, like Langevin, for example. Here, this is multiplicative, but it could be additive, multiplicative, doesn't matter. If it is a stochastic equation, I can always write down a generating functional, which is this quantity here. And this quantity is very useful because I can compute all kinds of observables that we usually want, like correlation function, I don't know, energy, entropy, all this kind of stuff can come out from this quantity here. It's the only thing that I would say. And I was particularly interested in applying this for out of equilibrium system, which the active matter systems they are. So, and specifically, I was interested in collective behavior, like why this kind of collective behavior appear, how can we describe it? So here we have some examples that are very well known, like the fish school, the flocking of birds, or the herd of sheep. They behave like this liquid state here, you can kind of say so. Or you can also have like different behaviors, like in non-microtubulus, or these puppies that behave, and I don't know how to describe this, okay? But it's all examples of collective behavior. But we need to start somewhere. And I started during the PhD with a very simple system, which is like the harmonic oscillator of active matter, because If you work in this area, everyone solve it at some point because it's really simple. So it's just a Brownian particle that diffuses stochastically, but it has a persistent velocity with a direction and an angle, right? And this is really simple. People know everything about this model, mostly. We know, for example, the trajectories, they increase the persistence with the velocity. People already categorize like biological swimmers and artificial swimmers. So this is very well known. Okay, but we need to start understanding how we're going to apply the formalism that I was learning to this kind of thing. And this is what I did. And okay, there is nothing really new here. We got the equations of motion, apply the formalism, and have an action. The action is nice, but I mean, okay, we have the translational degrees of freedom here, the orientational ones, and we have a coupling between the orientation and the position that happens because of activity. But from the practical point of view, nothing really new can get from here because they can get the same correlation functions people solve analytically by hand. And I mean, it's a complicated formalism for something that is really simple. So, okay, one particle we understand what is going on. So let's go for multi-particles, right? So then I describe the active particles with interaction now. And now things get more complicated because, okay, I can apply the formalism and I will have an action. Okay, so you just believe me that I apply, I get this thing. And this is an action for n particles, right? There is a summatory here. And again, I still have the translational degrees, the orientational ones. Now I have the addition of the interacting potential, but it still has the same structure of the single particle. And nothing stops us to study the action from the way it is here. But since I was biased for field theories, I have the question, okay, how I go from this particle action to a continuum action? Because I wanted to reach the continuum limit and describe some fields. And so this was the idea, right? How I get these active Brownian particles and reach something that is continuous. I know today that this is actually going from Newtonian description to a continuous theory of perfect fluid. So spoiler, right? But I will try to explain how this process is going on. We could do like a very honest guess and say that, okay, the labels of my particle is going to be mapped into a position vector into dimension space. At the same time, the position of the particle I will also behave like a field that depends on the position, and this sum will become an integral that is just normalized here by the density. Okay, this looks fine, but there's something weird here that at first you cannot see. So let me ask you a question. Do you believe that these two systems are the same or not? I just changed the labels of these two things here. So these are a bunch of particles. I just changed the label of the particles. Do you believe they are the same or not? They're indistinguishable, right? So in the particle sense, there is an invariance between label changes, right? And how does this invariance is being preserved in the field theory, right? Because now I can change the label and I'm going to the same position. So this for me is not very like clear. What is going on? What is the symmetries going on in the continuum limit? So we can actually do like a more general guess and say, okay, my labels now will be like a function. It's just a function that is smooth and invertible. The same is going to happen with the position. So now is like a transformation that depends on this function. And the integral now depends on the Jacobian matrix. Okay, this is really general. And what we usually want, working with the action, is that the action is invariant. And the only parameterization that will make the action invariant is my original guess. Because what is going on is that when the Jacobian is 1, what we have is the preservation of the area. So what we understand is that the parity invariance of the microscopic behavior translates into an area preserving in the continuum limit. So this is what's going on with the symmetry, because we are lost in the symmetry in the particle, going to the continuum, but the symmetry is being preserved when the Jacobian of the transformation is 1, and this is translated into a preservation of the area. So essentially, I put a sketch here. It's like in this mapping that I'm doing, is like separating an area, and if I change the labels inside the area, it doesn't really matter, as long as the area keeps preserved. So this is the emergent symmetry that we find out when we're going on for the continuum limit. And this is really useful because if you know that there is a symmetry, you can apply, for example, Noether's theorem and understand what is the conserved quantity of the system. And when you do this, you find out that it's exactly the same thing as the fluid vorticity in fluid books. So what we're seeing is that a formal description, okay, if I have a bunch of active particles, how do I describe this system of a bunch of active particles in a continuum limit? It's a fluid. It's literally a fluid. And if you know that the symmetry exists, we can find out in group theory what is the kind of symmetry, is the U1 symmetry, right? And you know, for example, how fluctuations behave in the symmetry. So I just put here the position of fluctuations. They behave like this pseudo vector A here, which is very useful because, okay, we understand the symmetry here, but there is another point that is very interesting, which is another consequence of the symmetry. Because up to this point, I was describing the system in the continuum in what we call a Newtonian or Lagrangian description, right? I'm describing the system from positions and velocities. If I want to describe the system from the density point of view, which we also do, is the Euler description. We can just use the single particle density. And this transformation, we find out that density fluctuations have a very particular structure. Yes?
That is from a permutation symmetry, right?
Yes.
And how do you make this step to vorticity? I don't know.
Okay, so.
What space does that operate?
Yeah, no, okay. So the point is, we perform this map, right? Actually, we perform the first one because this general one is general, but since we want to preserve the area, so this Jacobian here needs to be 1. So in fact, this is correct, right? So we are doing this map, transforming the positions, which are from the individual particles, into a vector. Y prime here. This is a general map, right? So I'm just saying that, okay, I'm doing a continual transformation, right? To this R. But this Y is general, depends on a function. And I can just say that this is another vector, another map. So it's just a generalization of a mapping. I'm just constructing a manifold in the space and saying that it describes the particle's position. This is the formal answer. But did I? Okay, so here F can be anything.
So anything.
Any function that is smooth and invertible is a function that describes this mapping. But we particularly choose just the mapping that is direct, because you can do this if you assume that the determinant is 1.
No, but you're going from Y to Y prime, right?
Yes.
You're saying Y is a function of Y prime.
Exactly.
And this function can be anything.
Any function?
Well,
yeah, okay, yeah. Anything that
anything reasonable.
Anything reasonable, yes.
But no matter what you choose, you get this U1 symmetry. I'm not.
No, the U1 symmetry only happens when you have the preservation of the area. Because we wanted the action to be invariant, and the action is only invariant when you have this preservation. And so this is something that emerged because of this choice of the mapping.
And the U1 symmetry is in what space?
Is in the continuous space. Is here in the continuous space. This
is a rotation, right? So how or no?
U1, yes.
So I don't understand.
The rotation is the charge that is being conserved in the symmetry. It's like in the electromagnetic description, right? This vorticity here is the charge conservation that comes from the Noether theorem. No, or
no? But what he don't understand and me neither is what is this? What is the action of the U1 symmetry? So you said that conserved charge is this one, but what is the symmetry?
The symmetry. No, the symmetry conserved is the area. What you call area.
But you call this U1? This is U2 in 2 dimensions, isn't it? Or well, I don't know. No, it's U1 times
because
U1.
It's circulate. Yes,
it's 2 circles, not 1.
Yeah, it's a circulation.
But under periodic boundary conditions.
Yes, circulation is the area, right? So it's this circulation.
Translation. Forward translation also preserves area.
The simple. No, because you need the velocity, right? If you don't have the velocity, you're not going to find out vorticity. At least in the particle. If you have a passive Brownian particles and you do the same, you still have the symmetry, but you won't find out a charge conservation in a passive description of particles. But the symmetry is still there. We actually did for both passive and active particles, and they still have the same symmetry because it's the mapping, right? The mapping is the symmetry. Yes?
I have a problem even before that. When you have the Horner's map, I don't understand that here.
Here?
Say why?
Yes.
Yeah, the Horner's guess.
Okay, yeah.
I is the label of particle.
I is the
You
label
say
of
the label of
particle,
particle, you compare it to Y, which is a coordinate.
which is coordinating a space that I'm creating. I create a space, a map, X, Y, and I'm saying that this Y will be transforming to a position in this space. This is a very simple guess, and it's true when you consider this bunch of things, but at first glance, there is the problem of the invariance of the labels.
The particular case, first one, is equivalent to f of y prime equals to y prime?
Yes. No, is equal to, is when y prime is equal to y.
What is the function f to reproduce the first case? F.
F is just y. So is when this equality is true, right? So it's just one.
So
Not
y
one, sorry,
equals to y prime.
Yes, y. Y equals to y prime, exactly.
But yeah, of course, this one Jacobian one, but there are
Yeah.
many transformations that have Jacobian one.
Yes.
Why you say this is the right one?
This is, no, I mean, this is not the right one, but this is the one that assumes that we have, I'm not saying here, but this is the one that we assume that we have a density homogeneous configuration. So you can show that this is, if there exists a stable homogeneous configuration, then the only option will be y equals to y1. Because we are assuming a homogeneous state. I was not telling this here, but if you assume that there is a homogeneous state, then this is going to be the transformation. Yes?
Is the statement then that in the discrete case, you want your system to be invariant under swapping the labels?
Yes.
And this translates to the continuous case where you have the same system whenever you have a diffeomorphism that preserves area.
Exactly.
This is the
This is the thing. Yeah.
Okay.
Any more questions? I don't know. Okay, so I was talking then the Euler description, right? So we can use the Euler, if you just use the Euler description, so instead of working with the Lagrangian one, the density one, we find out that we can smartly name these fluctuations of density like a magnetic field, although it's not a real magnetic field, it's just density fluctuations that has this structure. And okay, so this, just to recap, right? This was the particles action descriptions that we have. And in the continuum limit, we have this one for the position, the Lagrangian description. It's a little bit ugly, but it's just the mapping is direct here. I'm using the honest guess, right? So this would be the continuum action that describes this system. And the symmetry will be here. So if you look for this, for example, this first term here, you will find out the U1 symmetry is just right here. The conservation will be here, the conservation of area. Okay? And what we can do now is study actually the fate of the fluctuation. So we know how to describe fluctuations of this system because of the symmetry. So we can write an action for the fluctuations just to understand the fate of what's going on with the homogeneous state. And if you do this, you get exactly what it looks like electromagnetism's action, because B here is the fluctuations of density or the positions you'll find out. E is like the vorticity, is exactly the vorticity charge, because E depends on the omega of the vorticity. And here we have the coupling that is active. So if you don't have activity, you just don't have this coupling. But for passive particles, you have the first term. And okay, I mean, this is an action that is describing the fate of fluctuation. So you can start, but this is very general. We need to specify a model here to see what's going on, right? So we choose a very simple model, local potential. And when you consider the local potential, although it's not possible to simulate local potential, we just wanted to have like an idea what's going on. And the action localizes, much more simpler. And we can derive the equations of motion for this thing. And the point is that we have the equivalent Maxwell equations of motions for the active particles. So the point is we have n active particles that I'm going to the continuum limit. They behave like a liquid, a hydrodynamic regime. And I can have the equations of motion for this system, for the fluctuations of the system. And although it's a little bit complicated to solve this, especially with the local particles. I mean, I cannot simulate local interactions in particles. There is one thing that it was interesting at the point that you see that the charge, which I'm calling the charge here, which is just vorticity, it depends on activity. So if I have a passive Brownian a passive liquid with Brownian description, right? I will not have this thing here. So I cannot have circulations like the vorticity cannot happen in activity. And at the time, we didn't know, but actually Emilio and Cristobal have made our paper with the same model of active particles, which they simulate, and they find out, depending on the velocity, you find out exactly what I was expecting, which is the orientation becoming like a vortex, right? So for me, this was really fun, although it's not the same local potential. I mean, they use like a soft core repulsive interaction. If I do the same thing here for the non-local potential, I expect at least that this behavior will remain, right? So the idea of the vorticity, the electric charge appearing only when we have like the activity is something that people are seeing in the simulations. Actually, this another simulation that I found out just December of this last year is a paper that got out, which they get like mostly the same idea, and they did a simulation where they find out some vortex mediated by the topology and the symmetry here. So, okay, this was very nice for me at that point to see the simulations of something that I was going to see only analytically. And it was my idea, right? This was the idea to present. We can look for the actions and try to find out different things. For example, if you look only for the orientation of degrees of freedom, we can have something that is exactly like the Frank free energy for pneumatic liquids. So resembles a little bit, right? And we have the bending and display. So the formalism help us to look for other things that, for me, in the simulations, I don't know how to look for. So, I mean, for example, this free energy, I don't know how to get a free energy for the orientation of degrees of freedom, looking only for simulations. This was the first work that we did. This work that I was doing here, the FISC, is something I'm calling proliferating flocking model. And my original idea was also, how can I describe a continuum dynamics of particles that replicate? So now I want to include birth and death in the system and see what is the continuum limit. I did not use like any path integral approaches. I did something more traditional, which was just define a microscopic model, create the master equation, and then compute the mean field to get the continuum limit, right? So the microscopic model that I envision is like a lattice-based microscopic modeling, right? So the particles jump between grid cells, but now they also have orientation that is discretized. So the particles have discrete orientation. And okay, I define transitions rates for this process. The dynamics is just hopping in the two-dimensional grid, and the tumbling that is changing orientation. And we have here birth, competition, and death, which is do not preserve the mass. And okay, this is standard for statistical physics. So we compute like we define the master equation, define the transition rates, compute the mean field. What is important is that after all of this, the only thing that is not non-trivial is how do you include activity here? Because usually to include velocity in the microscopic model, we assume that the transition rates of the hopping are different between each site, even each direction. But if you do just this, if you just assume they are different, I could have a particle that has a pointing and it drifts in not the position they are pointing, right? So this is not activity. So the way you have to put activity in the microscopic rates is to do like a coupling with the angle of the particle. So now the particle have a probability to move to direction they is pointing. So you do this and okay, reach the continuum approximation, and we find out an equation for the density in the mean field continuum. And here we have the birth kernels, the competition, we have depth, diffusion, the rotational diffusion, and the activity. But again, this was very general, and I want to specify which model to test if the whole construction of the microscopic to the continuum was right or not. And we use like, just a point. This density is described by the position and the orientation, right? We can expand this in an angular mode to have like n equations, which the first one is going to be just the density, the first one, not the zero order, and the first order will be the polarization. So this simplifies a little bit the system, and I can treat things independently. But again, I was saying we need to test it. So we took like, for example, this paper from September of last year, when those guys, they assumed the active Brownian dynamics, like I mentioned before, but now they include birth and death, and the birth is non-local, depends on the number of individuals around. And I reproduce, the simulations, right? So for example, they discover many collective behaviors depending on the parameters. So we have here, for example, patterns, but with the polarization really close to zero because each cluster is pointing one direction. We have what they call flocking. So without any explicit alignment, it's just because of the birth. So the particles have a pattern and they flock. Here they are kind of homogeneous and also have a polarization. And this is completely disordered, homogeneous and disordered. So this was something that they noticed. I just reproduced the simulations to check everything. But the colors is the orientation, right? The orientation of the movement. So it's just the, the angle of the particle, right? So each particle has a color because of the part of the orientation that you're moving. So then we decided to test this. And to test this, we need to specify our interaction kernels. And so the birth kernels, they just assume that the birth is going to be local. So each particle that is giving birth, the particle birth with the same orientation as the father or mother, right? And the competition, well, each individual will compete with all other individuals in the area. So regardless of orientation, they will be competing with everyone. So you just assume this, and you simplify, you have these two equations here, right? An equation for density, an equation for polarization. And again, you see that the coupling between orientation and density is due because of the velocity. Here is written down on these three parameters, adimensional. So just to simplify the number of variables in the system. And we can just solve this question, so these equations, right? Because we have, if you don't have activity, this is just a non-local logistic growth with pattern formation. Everyone, I believe, know this. But when you have the activity, you have the coupling with the polarization, and we can start understanding what is going on. And if you do like a linear stability analysis on that thing, you find out, for example, you have a Turing instability in this black line and a Hopf instability in the red line. And I simulate this whole phase diagram, and you have this thing, right? So this green region is the region where we have pattern formation, so the density is growing. And you see that here the polarization. So this is the global polarization of the system. So you see that there is a region of patterns, but no polarization, and a region of patterns with polarization, so they are flocking. And this was the idea, to reproduce what people are seeing in the microscopic model. So this is a simulation in 1D, for example. You see here for the Hopf, the traveling patterns. We have a wave being propagated, and the density starts growing until the patterns form, and they all travel together in 1D. Here we have the pattern formation, but the polarization is positive and negative, and the system is stationary. So the global polarization is 0. And in the homogeneous case, we have the density constant around 1, and the polarization is really, really close to 0. And if you wait long enough, this at some point it needs to get to 0. But there is one behavior that is missing, which is the flocking and the homogeneous. And if you see here, for example, at the beginning, the polarization is really high, close to 1. But with time, it starts decreasing. So I believe that as a mean field, that behavior of flocking and homogeneous is probably not sustainable. You need probably fluctuations to sustain the homogeneous in flocking behavior. And we also did this for 2 dimensions because it was more interesting, right? Again, the same kind of map and also the simulations. You see here, this is the patterns with the topological defects, is stationary. And here we have patterns with a flocking, and the color again just tells you the direction of movement, right? This is like the homogeneous and disorder, is not really good to see because the amplitude is getting smaller. So, I mean, I don't know if it's that good to show this simulation here. But okay, this was mostly what we did for this project. We're still trying to finish some writing because the whole point was to find out a construction from individual particles to continual description that include this birth and death, right? And I think we managed to do it. So at least with this first test with something that has been published before, it is working. And okay, so yes?
So sinusoidal background or something?
No, is the disorder, I mean, this is
So what determines the wavelength of this oscillation?
what determines the wavelength of those oscillations is the characteristic frequency. Okay, so if you do the linear stability here in the model, you have a characteristic frequency of the oscillations from the eigenvalues, right? You can compute the eigenvalues and you... Exactly. So, okay. And okay, so I mean, we're trying to finish this, hopefully this month, I don't know. This is something that we plan to work this year. It's called active solids. It's something that is very trending right now. I will be brief just because, I don't know, not too much time. So just to be, let me try to play this. Just to be like very simple, one of the things people are interested in active solids is describing basically like how individuals move. Not everyone in the area is interested in this, right? A part of the area is interested in describing how things deform and change the shapes to adapt to the locomotion in the environment, right? So you see, for example, the starfish, which has no brains, and they move in this seafloor, adapting. And how they do this, like, okay, so you can look for the feet of the starfish, and it's kind of, there is like a traveling wave in the feet that makes them move. So some people are working with this. There is, for example, one research that studied this thing, and they characterize this movement like soliton propagating. So, okay, this is like the idea. People are interested in active solids. How do I pass here? And I want to go to something more simpler. Okay, I just want to understand the dynamics of the elastic phase transitions when you have activity mediated by phonons. What I want to do like this, let me try be very clear here. This is like a simulation that I found recently. So this is like a lattice, is a structure, right? And this guy did a simulation when he have like the, let me put the vectors here, the oscillations of this elastic system. And if you change, for example, the behavior, you see that the oscillations changes, right? So, okay, one thing that I would like to do is like a simulation like this to simulate these traveling waves, but including activity. Because, let me go back here. What is important? From what people know from theory of elastic theory of phase transitions, this is something from the 70s, it's very old. We have like the phonons, the equations of motion for phonons. And if you study criticality on this, you can change, for example, the structure, right? Imagine the shear forces in a solid. And depending on the shear forces, you can have elastic phase transitions where the system has a symmetry and it changes the symmetry because of the forces being applied. So this is people know this, people know how to study this critical behavior. I just wanted to do is to include activity in this equation of motion and see if I can find out anything about what is activities doing with these elastic phase transitions. It's a very simple question. I actually started working yesterday, so I have a general equation for motion that is stochastic. There is an active force here that is very general, and I will try to do, as I did the both ways, right? I'll try to write down the path integral for this thing, try find the correlation functions, how the correlation function changes for the criticality, and hopefully also do some simulations for this kind of thing. But this is something that is for this year, so it's just an idea for the moment. And I think it is it. Thank you all for the attention. That's all.
Okay, thank you, Nathan. So questions or comments?
A curiosity, what is a proliferating flocking modeling?
The proliferating is because we have birth and death going on in the system.
No, but which is the situation in which you have something that is doing flock mean movement and in
Yes.
while is proliferating?
Yes, because what we see, let me go to the simulation, it's probably here. So the flocking is happening, for example, in this one, right? Because the idea in the particles problem is you have a cluster. Because of the particle formation, they have a cluster. If a particle wants to deviate from the cluster, it doesn't have enough activity to migrate to the second one. So they die in this black region, right? So what we left is only with a cluster that flocks to the same behavior, because each particle that is being birthed has the same orientation. So inside the cluster, the particles already pointing in the same direction, and if they try to diverge, they will suffer the competition and will die. So in the microscopic model, the explanation for the flocking is because of that.
So you are thinking in microscopic.
Yeah, but in the your question was for the
Give me an example.
okay. So yeah, they propose like some bacteria that behave like this, okay, but but they propose some bacteria that behave like this flocking behavior.
What else?
I've become quite lost with in the first part of the
Okay.
talk with the questions of motion in terms of electric and magnetic field and all that, which are not vorticity and densities and all that. But there is something which worries me, is that the original equations of motion were first order in time. And now you have something which is second order in time in one of the questions you have written in terms of electric and magnetic field. Is
Yeah,
there
the density
this?
fluctuations are in second order, right?
Is this? Can this be true? I mean,
It was first order. Yeah, okay. This second order appears when I do the expansions of the interacting terms, right? So why this could be? I mean, it appears because of the fluctuations. You have a quadratic term there, but I don't know. Yeah, I don't know. I don't know how to answer this.
okay.
Because you think it is problematic because you have a second order in time fluctuation.
Yeah, in one case is everything is overdamped, and second order derivatives you have it's not overdamped. So I don't know. More questions or comments? If not, thank you, Nathan, again.